Wonderful. All right, so thank you everyone for coming to our Tech Talk. This is one in a regular series of Tech Talks the Arizona VFS chapter here holds for its members. I'd like to invite in technical experts from the field to give engaging technical seminars on the work that they're doing, keep everyone up to date on the field of research. But before we get started, just a couple announcements. Forum, obviously the annual forum's coming up May 20th, so I hope everyone's ready for that. And if you're in Arizona here, we do have dinner meetings regularly, so be on the lookout for those. Typically have them at Top Golf, dinner, golf afterwards, and a presentation in between. So it's a good night. We do have some STEM events around the area. We'll go to museums and collaborate with like the Commemorative Air Force, and we outreach to K through 12, and that's always a good time. We always need more volunteers, so be on the lookout for that. And obviously future Tech Talks. We got another one coming up on June 4th, human factors focused Tech Talk, but we're going to have more of those in the future as well. And then elections coming up. If you're interested in getting involved, you can reach out to our chapter president, Colton. I'm going to put our website in the chat, so feel free to find us there. Email if you want to get involved, if you want to position, if you want to run. We always could need more people, so feel free to reach out. Other than that, probably jump right into it. So today's talk, we have Dr. Nicholas J. Peters from NASA Ames. Dr. Peters earned his PhD from Embry-Riddle Aeronautical University in 2022. For his PhD, Dr. Peters collaborated with the HPCMP Create AV Helios development team at NASA Ames, focused on high-fidelity surrogate modeling for both fixed-wing and rotorcraft store separation. After completing his degree, Dr. Peters began working in the aeromechanics office at NASA Ames. His work at NASA Ames primarily involves utilizing high-performance computing to enhance vehicle modeling in the early stages of the conceptual design process. Key areas of interest include flight dynamics, turbulence modeling, automated grid generation, high-fidelity CFD rotorcraft performance predictions, and Rotorcraft Outwash. So with that, I will hand it over to, actually, not quite. Before I hand it over, we will have a little Q&A session at the end. If you want, if you have questions throughout, feel free to put them in the chat. We can read them off, or if you want to ask them in person, hold them until the end, and then we'll unmute you and let you ask your questions. So with that, I will hand it off to Dr. Peters. So, all yours.
Thank you, Carl. I appreciate that. I know when we met the other day, I said that we could go all the way through to the end and then ask questions at the end. Since it does seem like it's a smaller, maybe a little bit more intimate group here, it's fine if you have questions as we're going through. I'd be happy to answer any of those as we go along, or if you want to wait to the end for a Q&A session, fine with those either way. All right. So yeah, thank you first everybody for showing up today. Thank you, Carl, and everybody else over at the Arizona chapter for extending the invitation and giving me the chance here to talk a little bit about the work it is that we've been doing out here at Ames, specifically related to our CFD work related to rotorcraft-based outwash predictions. Before getting started, I do also want to acknowledge my co-author, Dorsa Shirazi. She was responsible for all of the comprehensive analysis solutions that we'll be showing in today's presentation. So without her, we wouldn't have had any of those results, and the paper definitely would have been hindered quite a bit. And I guess last thing to mention too, this talk is really an extension of the presentation that I had given a couple months ago now over at SciTech, where we had originally published these results. So if you have any questions further about the work after this, I can point you over to that paper as well. So with that, yeah, we can get started here. So this talk today is going to be all about the application of an actuator line-based CFD model for rotorcraft-based outwash predictions. We're going to first start out the talk, if I can get to the next slide. Oh, it's always the first challenge. There we go. So we're going to first start today's talk by going over a little bit about kind of what it is I mean by outwash in case you're not familiar with it. We're also going to go over what it is I mean exactly when I say an actuator line-based CFD model. We will then do a review, an overview of the study. So what it was we were hoping to achieve exactly in this work, along with how it was we went about exactly doing that. And then we'll show the key results that we had for our demonstration cases today. All right, so in this study, we were specifically interested in numerically modeling this phenomenon called outwash. Now, outwash is this outwards radial velocity that's being generated as the rotor's weight hinges on some ground plane and then turns and radially moves outwards. So we have a bit of an animation up here showing you that for some blade resolve CFD simulation that we ran over the course of the study of that weight, those tip vortices coming off that rotor blade, hitting that ground plane, turning, and then shooting outwards. And that outwards velocity that's being generated can oftentimes be quite large, especially for larger rotorcraft. That outwash can oftentimes be as high as gusts that you might see in either tropical storms or maybe even a Category 1 hurricane. So this is a very serious amount of outwash that can be generated and can be very limiting on to how exactly you can operate your rotorcraft in a safe way. So clearly it's something we want to have a good handle on before we start defining how it is exactly we're going to be operating our vehicles. Now, fortunately, at least for conventional rotorcraft, we've had a lot of experience with this problem, right? Outwash is not some new topic that came about in the past 2 or 3 years, but it's something we've clearly have been trying to tackle for decades now at this point. And it's really through this accumulated set of experience that we've gotten to this point where we do have a wide variety of numerical approaches to reasonably accurately, to varying degrees of fidelity, predict what that outwash is going to look like. Right? Of course, we can run our big high fidelity blade resolve CFD simulations, and then we can get some really nice predictions of the outwash. But we have enough data and we have enough experimental results to be able to also have lower fidelity tools that can reasonably accurately and very quickly tell you what your outwash flow field is going to look like. And so that's the good news, right? The downside, though, of all this is all that experience is based around more conventional rotorcraft, meaning some single rotor vehicle, like we're sort of showing here, or potentially tandem rotor vehicles, as we'll look at in this study, and side-by-side vehicles. But what we don't really have as much experience with are these new advanced air mobility aircraft. As we continue to see that field of AAM vehicles continue to mature and the topic of urban air mobility continue to mature, this subtopic of outwash is becoming a particularly challenging subtopic in the field to try and address. And this for a couple of reasons, but one real big reason here is that as we look into AAM aircraft, if you go up online, if you try and look at these vehicles, you're going to find out that every single one of them has a different number of rotors and a completely different rotor configuration. And it's really owing to that unique rotor configuration then that each one of these vehicles here is ultimately going to generate some unique outwash footprint. And really at this point, we have a limited amount of experimental data to help inform what exactly that outwash footprint is going to look like. Right. Now, in the absence of experimental data, oftentimes as engineers, right, we're being pushed to rely more and more heavily on our higher fidelity numerical modeling tools. And for us, right, that means relying on high fidelity blade resolved CFD simulations. And of course, it's pretty well known, right, that those simulation approaches, while they are very high fidelity, they're also very expensive in order to run. Even if we want to take one of these vehicles and do their forward flight or hovering rotor case, that will be, for a lot of folks, a prohibitively expensive simulation to run. Once we start talking about outwash, though, that becomes a particularly challenging simulation to run. What makes it so much more challenging is no longer are we just modeling sort of the weight right underneath the vehicle. Now we need to model and resolve this weight as it extends out possibly 4, 5 vehicle diameters away from the vehicle. Right? So we have this really big mesh count that we need to retain in order to run our CFD simulations. Another big problem is that for outwash, it takes a lot longer, a lot more rotor revs in order to build up this outwash flow field, a time repeating outwash flow field, as opposed to what it would take if you just want to get kind of what the weight was underneath the rotor, the weight immediately behind the rotor. Right? If we're talking about hovering rotor sims, depending on which paper you read and what level of fidelity you want, you might want to run like let's say 20 revs. But if you want to be able to model a time repeating outwash wake out to about, let's say 4 diameters away from the vehicle, you're probably going to need running more like 40, maybe 60, or we've even seen in some studies up to 80 revs, depending on what conditions you're exactly under. All right, so obviously that is just a computational cost that is sort of beyond the capabilities of a lot of analysis groups that really need to be able to model outwash with the highest degree of fidelity that they can. So clearly we need to have an approach which retains as much of the modeling fidelity as possible as these blade resolve simulations, all at a greatly reduced computational expense. And not only that, but we would also like to be able to stay as long as we can, right, within this CFD modeling environment that we're sort of already used to, right? A modeling environment where we can have nice body-fitted grids for our wings or for our pylons or for unique fuselages we might want to analyze, or maybe have a nice mesh down by the wall so that way we can get shear stresses if we need to. So we would like to be able to stay within that environment, and we would like to be able to reduce the cost to stay in that CFD modeling environment. And sort of the point of this study then was to see if actuator line-based CFD modeling would be a viable approach to reducing that cost, that sort of barrier to entry to CFD outwash predictions, and seeing if we would be able to do that or not. All right, so sort of before going on and talking about the study too much more, or looking at any results, I do want to at least highlight what it is I mean by an actuator line-based CFD model. That might not be intuitive to everyone in the call. So really all I mean when I'm saying that is that you've gone through, you've taken some blade element theory code that either you wrote or you coupled together with some external solver, and you've implemented that within your CFD code. Right, and then what you do is you'll go to every one of your blade elements that you have on that blade, on every one of your blades, and you'll extract out from the surrounding flow field what are the induced velocities, the CFD computed induced velocities at every one of those blade elements. We'll then go through and use those induced velocities to try and identify what are the loads at every one of those blade elements. You then convert those loads into source terms for your Navier-Stokes equations, both the energy and momentum equations, add them into your CFD solver, time step the solution, and well, there you go. Hopefully get a decent representation of this unsteady time evolving wake that's coming off the rotor. Now, there's a couple of reasons as to why you would want to do this. And sort of one of the big ones is that, well, it greatly reduces what is the difficulty of setting up one of these simulations, right? If you're going to have a blade resolve CFD simulation, there is a very particular way that you need to make the mesh for that rotor. It is a lot less forgiving to try and set up a blade resolved grid, right? That's one challenge. Another challenge is, especially if we're talking about a solver like OVERFLOW, an overset structured grid based solver. It is also even more challenging to try and set up one of these grids for overset based structured grids for your rotor blades. It is much more difficult to try and set up one of those blade resolve meshes as opposed to simply setting up one of these line models, something that is either very easy for you to set up manually or completely automated if you look towards a lot of other solvers that have blade element solvers implemented within them. So it helps you to get up and running with your simulations much faster, right? It allows more people to get up and running. The other thing that it does is that because we're not resolving this complicated grid, we can end up resulting in a much lower mesh count required to run your actuator line simulation as opposed to trying to run a blade resolve solution. We can also typically run with much higher time steps with an actuator line model as opposed to what we would traditionally run with our blade resolve solutions. And so that all sort of comes together to make a solution that's not just easier to get up and running with, but also runs much, much faster. As we look throughout the literature at a variety of different solvers, sure, the time difference changes from paper to paper you look at, but it's quite consistent that you can expect well over an order of magnitude in cost savings by running an actuator line model as opposed to a blade resolved CFD solution. All right. Now that's the good, but there's obviously some downsides to this, right? The downside of implementing an actuator line model is that while we've replaced the sort of first principles approach of modeling our rotor blade with a line model, right? We're back to using a more simplified representation of our rotor that we could have already implemented in some other solver. So sort of what we needed to be able to identify then in this study, was there an advantage then of applying this blade element theory model, this actuator line-based CFD model for outwash predictions, as opposed to maybe potentially other options that are available out there for you in the field? All right, so with that, hopefully we have a okay understanding of sort of what it is that we're talking about when we say an actuator line model, and hopefully we kind of have an idea as to what outwash is and why it's sort of important. We'll now take a bit of an overview of our study before looking at our key results. Okay, so in this study, sort of our first step that we did is we went through and we tried to implement an actuator line model within the OVERFLOW CFD code. OVERFLOW is a commonly used Rotorcraft CFD tool that is commonly used in the Rotorcraft community. It's a software that has it's been shown to get very good predictions for blade resolve solutions. It's also a solver that already has a disk model that's been implemented within it and nicely validated as well. And so what we were trying to see is we could kind of hit that in-between point between actuator disk modeling and blade resolve modeling and implement this actuator line model. Once we implemented this model, the first thing we wanted to do was validate this model could get you meaningful and useful predictions for time averaged rotor wakes for a series of progressively more challenging to model cases. So the first case that we looked at was a single rotor hovering out of ground effect, just the simplest modeling case that we could look at for a rotor's wake. And this sort of allowed us to have a little bit of an initial baseline to just make sure that let's just get a baseline understanding as to how well this model can potentially work in the simplest of cases. The next case that we looked at was a single rotor hovering in-ground effect. This was sort of our first outwash validation effort with this line model. And that sort of let us get a baseline of understanding of how good the model would work for a relatively simple outwash case. But then the last one that we need to look at was a multi-rotor configuration. So we looked at a tandem rotor configuration and tried to see if the line model could still match up reasonably well against experimental measurements. All right, so that's sort of what the three cases were we were looking at, right? But as I was saying before, this line model doesn't exist in isolation in this field of time average rotor wake predictions, right? There's a lot of tools at this point that will let you do that. And so what we needed to see was how well does this line model compare to those tools in terms of both modeling fidelity and computational cost. So by comparing this line model to sort of the higher end fidelity of the spectrum, right, we wanted to see how it compared to sort of the best solutions that you're going to be able to obtain, which would be a blade resolve CFD solution. So we were comparing against those runs as well for all 30 of those cases. But we also have other options that exist outside of this CFD computing environment. So what we also need to kind of answer was, if your analysis permits you to leave this CFD computing design space, how well does this line model compare to a lower fidelity tool in a comprehensive analysis-based solution? And for that stand-in, we were using the CHARM solver, right? A solver that has been shown to work quite reasonably well for time average wake predictions and for outwash predictions as well. All right, so to compare these solvers to the experiment and to one another, for the downwash, the out of ground effect downwash case, we were first, for the CFD solutions at least, running an initial 20 rotor revolutions. That initial 20 rotor revolutions allowed us to build up an initial time repeating downwash wake. We then ran an additional 10 rotor revolutions, so that way we could have enough data for time averaging. With that time average wake, we then went 4 different radial distances beneath the rotor's hub. We extracted out the induced velocities, and then we used those induced velocities to compare between experimental measurements and the three numerical modeling approaches. For our outwash case, we did something kind of similar, but a little bit different. Like I said, we had to run a couple more rotor revs to build up this time repeating outwash wake. Even for the two diameters that we were looking away from the rotor's hub, we still needed to run for an initial 30 rotor revolutions to build up this time repeating wake. After that, we ran an additional 10 rotor revolutions so that way we would have enough time averaged or time series of data, sufficient time series of data for getting a good average flow field within that sort of two diameters away from the hub. Now, once we had that time average data, there was a couple of different metrics that we looked at in the paper. For the sake of time today, we're going to be focusing in on sort of our two key metrics that really help get the idea across in today's presentation. The first one that we'll be looking at is time averaged maximum outwash as we move radially away from the rotor's hub. That will be the first one that we'll look at. The second one that we're going to be taking a look at is using something called the Paxman model. Now, if you haven't previously heard of the Paxman model, this Paxman model is a commonly used outwash metric that's used in the field. It is a modeling approach where we try and take our outwash flow field and get an idea as to what would the force be on somebody who might be standing crunched over in this outwash flow field. The Paxman model works by first having a polynomial function whose coefficients have been prior determined based off experimental measurements. Once we have that cross-sectional area, we then either run a numerical simulation or an experiment. We take this outwash flow field that we get, and then we integrate that outwash field over that person's height. And with that, it can give us a nice idea as to what would the force then be on somebody who would be a ground crew member, let's say, operating near this flow field. Okay, and so perhaps a little bit more of a practical way of analyzing how in the field these analysis techniques would be useful or not. All right, so those are the metrics that we were looking at, sort of what it was we were doing in the study. We'll now take a look through what are the three key demonstration cases that we have lined up for today. Starting first with our single rotor out-of-ground effect case, right? Our initial baseline case to just get an idea as to what's the relative computational cost and what's the relative fidelity, even in the simplest case setup. All right. So in this case, we were modeling a relatively simple three-bladed rotor, isolated by itself, modeled roughly more or less based off the front rotor of CH-47. We ran that simulation, again, 20 revs, an additional 10 revolutions for time averaging. And then we compared what our wakes were that we were predicting between blade resolve, actuator line, and comprehensive analysis. Now, before taking a look at those results, as we said, we didn't just want to compare fidelity. We also wanted to compare what was the relative computational expense between these three approaches. And we summarized that table. Well, we provided a summary table for you here in this slide here for you. So in that table, we're showing the cost for all three of those approaches that was used for the study. I should mention that there are a lot of caveats that are associated with this table, right? I mean, as there inevitably are going to be when we're comparing different numerical modeling approaches, or even if you're comparing different computational hardware, there will always be caveats. We do spend a decent amount of time in the paper, I will say, reviewing those caveats. And I'm very happy to answer any questions or provide any extra context after kind of wrap up here with whatever questions you got. But I still want to include this for each one of our cases that we have, because the relative cost comparison between blade resolve, actuator line, and comprehensive analysis is very consistent with what it is that you're going to find in the literature as you compare these three modeling approaches. It is not an outrageous statement to say that if you're going to be running a high fidelity blade resolve solution, yeah, that's probably going to take you, depending on how you parallelize things, it will probably take you that amount of 4 hours to run. We ran with a little over 1,000 CPUs, and that took us a little more than, well, about 3 days to run, about 3 days. And that's a computational cost rate that is out of reach for a lot of folks, right? A lot of folks are not going to have access to that sort of resources on their local clusters in order to run. And if you want to consider running that on a system like AWS, that can quickly become a very costly, expensive simulation to run and perhaps difficult to justify, depending on which, I guess, analysis group you're exactly in. Now, we can see, though, as we move over towards our actuator line model, the cost here has been reduced by well over an order of magnitude, right? We're now talking about a CPU count that is much more accessible to folks. And a total time to run that in the end, when we get our core hours, that it is definitely a much less expensive simulation to run on a system like AWS or whatever your server provider is of preference. Right, so good. We're sort of able to kind of hit that first goal that we had of reducing the cost. All right, good. But we can also see here from this table that if you are willing and able to move away from your CFD analysis and use a comprehensive analysis solver, if your design space allows that, then you can clearly achieve far greater reductions in expense, right? All of a sudden, we gone from something that still needs to run on some remote server somewhere to something that can run quite efficiently on your local laptop. And I should also mention that Dorsa was really showing off the capabilities of these comprehensive analysis solvers by running far more revs than what it was I was ever going to be able to run with a blade resolve solution in CFD. So we kind of get the picture here, right? We go from a solution with blade resolve that's perhaps inaccessible to a lot of folks to an actuator line modeling approach, which is quite accessible to a lot of people, but still requires some solid compute hardware, to a solution approach and a comprehensive analysis space that is much more accessible to people, and particularly is very attractive when you're in the earlier stages of your design process. All right, so with that, that's probably enough context of your comparative computational expense. Now we'll take a look through what was the comparison in the induced velocities to the time average wakes for the sort of baseline out of ground effect case between our three different modeling approaches. We are showing 4 different slices into the wake, starting with our closest slice being about 40% of a radius underneath that rotor's hub, and then going all the way out to a little over a diameter and a half away from the hub into the rotor's wake. The y-axis here is showing the induced velocity normalized by VH. So VH is the momentum theory based induced velocities. And then the x-axis is the radial distance outwards from the rotor's hub, starting from the rotor's root at a root cut of about 20% out towards the rotor's tip, R over R1. All right, comparing our numerical modeling approaches, right, between the 2 CFD modeling approaches, we see that both approaches were really providing a very nice comparison between the 2 of them, right? They were tracking with one another incredibly well, especially considering this huge reduction in expense that was being achieved, right? Despite well over an order of magnitude reduction in expense, we are still consistently tracking well with what it is that we would have gotten for blade resolved, at least in this baseline case, and at least for the metrics that we're showing so far in this study. This actuator line approach does seem to be quite attractive for time averaged rotor wake predictions, which is good news. But we also see that the comprehensive analysis solution is still very nicely providing some very meaningful solutions for that time averaged wake, especially when we consider that huge reduction in expense between moving from CFD to comprehensive analysis. We see that the comprehensive analysis solution is far more attractive to run, again, particularly when you're in these earlier stages of your analysis, and speed and cost is really of your analysis is weighted much more. All right, so with that, I think we've hit on a lot of repeating themes that we're going to end up seeing a lot later on in this presentation with these next 2 cases that we looked at. But again, that was sort of the results that we had for our out of ground effect case, our simplified baseline case. We sort of got the picture that blade resolved and actuator line track quite nicely with one another, but there's a huge reduction in cost between the 2. And we also see that there's comprehensive analysis solutions are nothing to scoff at. But what we need to show next is our out of ground effect or our in ground effect outwash cases and really get to the meat of the problem here. And the first one that we're going to start out with is this single isolated rotor hovering in ground effect. So in this case, we were modeling a single isolated rotor hovering roughly 1 radii off the ground. And we were running this simulation, again, running our 3 numerical modeling approaches. We ran our 30 rotor revolutions and time averaged over 10 of them. We're going to take a look at our metrics here in a minute, comparing the accuracy of these 3 approaches. But again, we will briefly talk about the comparative computational costs between these approaches. Now, yes, the trends between all 3 of them remain the same, right? Good. We see blade resolve is still very expensive. Actuator line is a couple orders of magnitude cheaper in expense to run, and comprehensive analysis is by far the cheaper option, unsurprisingly, right? But what I do want to highlight here is that when we were talking about this all in the introduction, I was mentioning that these outwash simulations are much more expensive in CFD to model compared to what it is that you would model for an out-of-ground effect case, right? We're no longer just modeling that wake right underneath the rotor. We're now modeling a wake that can extend out many diameters away from that rotor's hub. That's a huge amount of mesh that we might need to retain. And we can see that reflected in this cost, right? As before, we probably were running our blade resolve solutions for about a little less than 3 days. Now we've over doubled the time to run that numerical simulation. And that was really true for all of these. The cost either doubled or significantly increased as we went from running our out-of-ground effect cases to our outwash cases. So really highlighting the challenge in trying to run these cases. All right, so with that, we'll now take a look through the results that we have for the single rotor case to present today. On the left of your screen, we are showing the time averaged maximum outwash. The y-axis is that time averaged maximum outwash normalized by the momentum theory based induced velocities, VH. And then the x-axis is that radial distance from the rotor's hub. So R over the diameter, so normalized by the diameter of the rotor. So we're extending out to about 2 diameters away from the hub. The right plot that you're seeing is the results of that integrated outwash. So the Paxman integrated forces, where the y-axis is the integrated force, and the x-axis is how many diameters away we're sort of extending at each one of those points. All right, so first, kind of comparing our 2 CFD approaches, we see that once again, really with both of our metrics, both of those CFD approaches are comparing with each other quite nicely. The actuator line approach and blade resolved approach for this time averaged maximum outwash, both of them track with one another quite nicely. And they also are tracking quite nicely with that mean experimental measurements. And then when we further integrate that outwash flow field with the use of the Paxman model, well, we see that both of those CFD approaches, at least for that boundary layer height from the floor to about 5.5 feet, really end up with a near indistinguishable solution between the 2 of them, right? And this, again, was despite this huge reduction in expense that was being achieved, really highlighting that, yes, if you want to stay within the CFD modeling domain, if your analysis really warrants that, actuator line approaches, at least for the metrics that we're showing here, are a very good alternative for you and can really help save a lot of expense and potentially a lot of difficulty in setting up those simulations as well. The last thing I'd like to mention here, though, as well, before we move on, is that the charm model is not performing particularly bad either, right? Sure, we sort of, for the time average maximum outwash, you could argue when you get out to 2 diameters away, okay, we're outside the bounds of uncertainty. Those bounds of uncertainty are already pretty large as is. But, okay, well, charm is an inviscid solver, and really, maybe that's not the best metric to be looking at anyways for charm. If you integrate that outwash profile, you see that, yes, you're within the bounds of uncertainty consistently with the charm model, with your Paxman forces, and it's definitely a very meaningful prediction, especially when you're considering just how fast it is that solution can run, right? And especially if you're in sort of the earlier stages of your design process, And your analysis is a lot more waiting on the turnaround time that you can get your results in. All right, so that's all good and everything, right? That's good context. But again, that case is not exactly representative, though, of these AAM aircraft that we were sort of targeting all along anyways. Right, so what we need to be able to show next as a sort of final validation study is that the actuator line model would still provide and compare well once you include a second rotor, right? So once we sort of have one of our more challenging cases that we could look at, right? And so in this case, we were modeling the tandem rotor configuration of a CH-47, so no fuselage, just the rotors themselves. And this is a bit more challenging a case to run for us, right? We're talking about running not just one rotor, but two rotors, so the size of our domain is starting to increase, right? And that is reflective in that computational cost table, as the cost to run those simulations has now been increased. We also have rotors that are intermeshed. So we have rotors that the blades are passing sort of in and out of one another's wake. So really pushing how good your models actually are performing. All right, so that's what it is that we were modeling in this case. The one thing that is a little bit different between the single rotor case and the tandem rotor case is that in this tandem rotor case, instead of looking at the outwash as a function of the radial distance from the rotor's hub, we're instead looking at the distance from the rotor's center line. So looking from this vehicle center line towards the starboard direction, and then so like kind of where these rotors are rotating towards, and then the port side where these rotors are rotating away from. And by looking at this plane here, the center line plane, we're able to get an idea as to how well we're able to model this pretty complicated to capture rotor interface plane. Right. This is really the challenging part and really the thing that we can use to sort of test out how good our tools can work. All right, so with that, we'll now take a look at the port side and the starboard side predictions that we have for time average to maximum outwash. Again, y-axis, again, showing time average maximum outwash normalized by VH. And then the x-axis, again, going about 2 diameters away from the center line of the vehicle. And what we sort of see here are 2 different stories being told. When we look at our port side predictions, we see that all 3 numerical approaches are actually tracking quite nicely with one another, and they also track quite well with those experimental measurements. On the starboard side, though, we see a little bit different of a story being told than what we've been seeing so far. On the starboard side, we see that while both blade resolved and charm actually match really, really nicely, the actuator line model is under predicting what that outwash is going to be, that maximum peak outwash in the boundary layer. And unfortunately, as we continue to go through and integrate these outwash predictions through the use of the Paxman model, we see that story really holds true. On the port side, all 3 approaches track quite nicely with one another, quite reasonably well. The starboard side, though, once again, on this side, we're seeing a consistent under prediction in that outwash that we were getting, really throughout that 0 to 5.5 foot boundary layer. Now, ultimately, since SciTech, when we looked at this, there's a couple things that we've been trying to track down, right? There's a lot of potential reasons as to why we had this under prediction and outwash. And we're still trying to figure out exactly what was causing that. One thing that you do end up noticing is that in that overset region between the interlocking of those 2 rotors, when you're on the port side, you have a very nice comparison of the rotor load predictions in that interlapped region, but in the overlapped region on the starboard side, we did see an under prediction in the thrust coefficient for the actuator line model, which could mean that maybe we didn't set up our blade element model all good enough to operate like in that region. It could also be that, okay, this is an underlying model. There's a lot of things that go into it. We maybe didn't extract the induced velocities in the best way possible. That's always a question with these actuator line models, extracting induced velocities from CFD solutions. We also maybe just weren't distributing that source term back into the Navier-Stokes equations in the best way that we could have been doing. There's a lot of options available to you as to how exactly you do that. So maybe the option that we picked just wasn't the best in this case. So clearly more work is done, needs to be done, right, to sort of track down that error exactly. But nonetheless, sort of going on to these concluding remarks here before we go into our Q&A session, we kind of look back to what our initial goals were that we had when we set out with this study. It was to be able to implement this new line model into the overflow CFD code, and then being able to demonstrate that with this model, you could get very reasonable predictions for what your outwash was going to look like compared to an experiment, all at a greatly reduced cost. And in the end, pretty consistently with all three of our demonstration cases that we looked at, we found that we really were able to achieve those objectives, right? For both the out-of-ground effect, in-ground effect, and tandem rotor case, we were almost always within the uncertainty bounds of the experiment, and our cost was also very reasonable that we were getting. Right. We also saw that that cost for the line model was much lower than that of the blade resolve model, all while by and large staying quite consistent with the level of fidelity, at least for the metrics we were looking at. And then the last thing we sort of showed was that, okay, that was nice and all, but we also showed that if your analysis permitted you to sort of leave this CFD modeling environment that you were in, you could get some very nice predictions for the time average outwash, at least the metrics that we were looking at in this study, using a comprehensive analysis-based approach. In this study, we were using CHARM, and that was a very meaningful solution as well. Sort of one of the last things I want to kind of sign off with here too, at least this slide, is that this line model that we implemented is still a NASA internal model. So if you download the latest release of OVERFLOW, it is not included quite yet. There are plans to include that in a future release. I'm not going to commit to a time frame on when that is going to be released, but we're working through the software release process. And we're also going through and trying to validate out the model for more than just outwash, so that way we can kind of demonstrate some best practices with the model for a variety of different rotorcraft applications. All right, so with that, I'd just like to also acknowledge that this project was supported within NASA by RVLT management. So thank you to them for their funding support. I work over at the aeromechanics office at NASA Ames, so I'd like to thank everybody over there. They helped me out quite a bit with getting up to speed on this outwash problem since it came out to Ames and started working on the problem. And then also Peter, Joe, and Chip over with the OVERFLOW development team. They were a huge help in understanding the workflow of OVERFLOW and understanding how to work with it and their support in that. So yeah, with that, I'd be very happy to answer any questions. Thank you everybody for showing up to this talk, and hopefully you all found it interesting. I see Rick, you have a question.
Hey Nicholas, thank you so much for giving this talk. Yeah, this is Rick Derez, Boeing Aerodynamics. As you were going through the presentation, I was scratching my head on thinking about, well, I wonder how the actuator line model would be, like how the tip vortices form using that paradigm. And it kind of looked like on the tandem rotor case, when you were showing the vorticity comparisons, that the vortices sort of disappeared earlier on the actuator line side. And so I was kind of wondering, did you look at the vortex strength compared to the blade resolve, and maybe there was even some test data in it, and could like the weaker vortices that maybe break down earlier, could that have caused the underprediction in the max outwash velocities?
Yeah, thanks for bringing up that point. That's definitely a good point. We didn't address that in this talk here. I will say in the paper, we do have a bit kind of going into that discussion. So before even talking about the, let's see, I might actually in the backup slides, depending on how I remade these backup slides, have something there. Okay, yeah, sure. Here, a bit, right? So here in this figure, to kind of preface a little bit, I guess, the discussion. This is one of the figures taken from the paper comparing both blade resolved out of ground effect and actuator line in ground effect. You can definitely, so we're looking at a side plane. So the ZY plane, and then we took a slice down the middle for vorticity magnitude, kind of grayscaled that. I showed isosurfaces of Q criterion, so that way hopefully you can kind of see how that sort of slice translates to a 3D space. And as you can see, kind of to your point, right, the actuator line model, that tip vortex that's coming off is far more smoothened out compared to what it was that we were getting with our blade resolved model. Right, with our blade resolved model, there's obviously a lot of differences as to how that vortex is forming compared to an actuator line model. So one thing that we go into in the paper, maybe would have been nice if I had, see if I have it on the next slide. I don't. Is that if you look at that tip of the rotor, right, that vortex, you don't just have one vortex that comes off the tip. You have one vortex that comes off the bottom half face of the tip, and then you have another one that forms the top half face of the tip. They sort of form together, and then you have the shear layer too, and next thing you know, you have a vortex that is forming very different than the line model, where, okay, we just have a line, and then the flow just forms one vortex around that line. So you do have to be a little bit careful that the vortex itself is even forming different. And then on top of that, another thing of concern is that ultimately you are taking your source term and you have to find some way to spread it out over a local cluster of cells. Whether you do that through doing that in the chordwise direction, you have some volume of space that you're distributing it over, or you just select a cluster of local points and just dump them in there. And every one of those ways that you select is going to have a pretty big influence as to how smooth out this weight ends up becoming. So I think within this paper, and I think you're hitting a good point here, we may have just been introducing that source term a little bit too spread out, a little bit too far, and that might have been resulting in a tip vortex that was a lot smoother than perhaps it should have been. I think also, since we were just sort of starting out with the model, I think that there was a lot of things that we didn't quite fully appreciate that could change that wake. I can say that as we've sort of been going through now and attempting to validate this model out further, taking your time with it a little bit more, we're doing a bit more sensitivity studies. What is the mesh refinement exactly up at the tip? What time steps are you exactly running with? Along with some other terms too, right? Like how far are you smoothing out this flow field? What's your method exactly that you're taking for extracting those induced velocities? Because there's a lot of methods available out there. We're finding that all of that, to varying degrees, end up pretty significantly affecting the wake and end up significantly affecting the loads that you end up predicting as well. So I think we're still working our way through the best practices there on that, but I think you're hitting a good point there that at the end of the day, this is an underlying model. It's a simplified model with a lot of terms in it, so you have to be a bit careful about how you tweak those terms exactly. Sorry, hopefully that rambling kind of addresses it.
Yeah. Yeah, thank you very much.
Yeah, thanks. And we actually have a question in the chat from Ted here. He says, very nice work. How does the new model differ from the legacy overflow model, BC 145?
If I recall right, BC 145 was, okay, you're gonna have to correct me if I'm wrong here. Was that the actuator disk model, not the new blade element actuator disk model, but just a prescribed load model?
Yeah, hi, this is Ted Metcroft. So 145 is a momentum source rotor disk model. So it's using blade element theory to compute a force term for each node in the in the rotor disk, and then it converts it to a momentum and an energy source term for solving in the CFD part of the model.
Okay, yeah, thanks for clarifying that. Yeah, it's a very similar approach, right? Whether it's a disk model or it's the blade element disk model or it's an actuator line model, the fundamentals of it are almost exactly the same. You get a source term, you go to your cells that you're at, and you distribute it over those cells. I guess the difference here is that we are actually modeling the individual blades of that rotor disk, I guess. Let's see if I can go back and. All right.
Yeah, so you're not time averaging it. You're actually the sources are moving at the rotor speed, at the rotational speed of the rotor blades.
Exactly right. So we go through and we implement the a single grid block for every one of those blades. We then go through, just as you would with the disk model, right? Except the disk model, you have one grid for the whole rotor system. Here we have one grid for every blade. We then go through, we make sure that we communicate to overflow that, okay, all these blades are connected to one another so we can compute the loads. But the source terms are only being applied to every one of those blades, kind of along the, let's see, the next slide, I think should have a bit better, along sort of like that line where the blade is at. So we'll go across every one of those J nodes in the Y direction, which we're showing here. We'll extract what the induced velocities are. We'll go through our blade element code that we've implemented. And then we'll go back and distribute our source terms over that sort of local cluster of cells using kind of a Gaussian distribution. I think that I'm not sure how BC145 did exactly. I know that the disk model just applies the terms over that one disk. I tried to apply it just along that one line. I was running into a lot of stability problems. So I found it a lot more stable of a solution if I could kind of smoothly distribute over a local cluster of cells. I just kind of go through the root to tip and I do it that way. And then that whole blade is rotating as the sim is running, just as you would with your blade resolve simulation.
Okay, thank you.
Thanks. And I see we have another hand raised. Rick.
I'll keep asking questions if no one else has them. So I was curious, for Outwash, is frequency content important? And if so, how well did the actuator line model do compared to blade resolve or experiment?
Yeah, that's a good question. I think that the short answer is don't know 100%, right? We don't know 100%, but yeah, it can be pretty important, right? And I think that maybe a question before even answering the frequency content is that, we were looking at time averaged outwash, but there's a pretty big difference between what your time averaged outwash is and what your peak outwash is, right? Depending on what rotorcraft you're looking at, and depending on where you're looking at exactly, your peak gust that you have coming through could maybe be like twice what the size is of your time average. So sure, you're not going to knock someone over with the time average flow, but if you have a big gust that rolls through, you definitely could. I'm sort of playing this animation to show you that, yeah, that's sort of what ends up happening. You end up having, I'm not sure if you can see my mouse or not, but you sort of look at these tip vortices. Okay, good. As you see these vortices coming down, the tip vortices they come down very quick. They slow down though, and they sort of more or less collide together. I mean, I guess it's not 100% certain exactly, but I'm going to take some liberty and say that they come down, they combine together, and then they sort of stretch out, right? They sort of move out, and you get these much larger rings that move out at some certain more or less fixed frequency. And you get these big intervals of high gusts that end up being able to be shot out. And I guess it depends on what it is you're exactly strapping down. But yeah, I think to answer your question in short, I bet hopefully I addressed your question. There's definitely a lot more to outwash than what we were looking at in this study. I also would say I think it's important that when you're talking about AAM aircraft, we're not just talking about urban air mobility. The space that these vehicles could be operating in has sort of expanded, right? And yes, if you're talking about UAM, you're really just talking about outwash, but eventually you might not just be talking about outwash, you might be talking about brownout. And in that case, you're not just talking about what's your integrated force, right? Because if you're using the Paxman model, it doesn't really matter what the shear stress is of the wall. But if you're talking about brownout or whiteout, yeah, that is going to matter quite a bit more. So I think that there are still a lot of metrics that sort of need to be nailed down here a bit better than was done sort of in the time frame that we had in this paper.
All right, very good. Thanks.
Yeah, Rick, if you want to keep going, we got time for maybe one or two more.
All right. Yeah, I got another. So I'm I'm scratching my head thinking, okay, we saw that plot showing the charm predictions for the tandem case, did a really good job on the velocity and the integrated load, the integrated forces for the computational cost. So I'm thinking, well, what are some applications like maybe certain UAM configurations where the vortex wake approach just will not give a useful result, and to show like that, because that's where the actuator line CFD would bring value, right? So I was wondering if you knew of any configurations where maybe like when you've got 4 rotors, then the vortex wake really starts to fail based on past attempts. Yeah, are there any that are known?
Any that are known? I don't think anybody should be able to come forward with 100% certainty and be able to say that charm would not work, or there's a modeling approach that is the absolute best for these vehicles that I'm showing here. And the reason why is because it comes to the biggest problem that we have right now. We don't have experimental data for these aircraft, or at least the experimental data that we do have is quite limited, right? And we don't have maybe as careful set up experiments as we do, let's just say, for a single rotor, right? I mean, if you want to find out what's the very best modeling approach for a single rotor vehicle, then all right, you can do that because there's been an enormous amount of experimental data for single rotors. Tandem rotors, Mark Silva and his co-author did a fantastic job of collecting really good experimental data for the CH-47. So you can get a tandem rotor and you can compare in this exercise here these different modeling approaches. You can't really do the same with any of these aircraft because we just don't have nailed down 100% the same level of experimental data. So we can try out different approaches. We can see differences in the technique. And I mean, there are things to be concerned about, right? We're not talking about just 1 or 2 rotors where we're going to have some really strong tip forces. We're talking about rotors where, I mean, these things are going to be pretty close to one another. Looking at this lift plus cruise here at the top, there's a big pylon that's here. There's a wing that's going to have interference. There's this big fuselage down the middle. Or especially if you go over to this, the bottom vehicle here. Again, there's a pretty big difference in setup between this and something like a CH-47. And will the charm model be the best model? I don't know. I also don't know if there's an easy way to say if it would be or wouldn't be. Would the line model and blade results still compare as well? I hope so, but I don't know for sure. And there's a lot of other approaches out there beyond the vortex panel method approach, right? We can say, does the vortex particle method, VVPM, is that going to be the better approach? Or if you listen to Richard Brown and see his good work that he's doing with vortex transport method, maybe that's interesting. Or maybe as people are revisiting Lattice-Boltzmann, maybe that's an interesting approach for outwash and sort of satisfies your concerns. I think there's a lot of competing solution approaches that are out there. but I'm gonna sidestep here and talk about a little bit of what I was saying in the beginning. Because there is so much uncertainty, that sort of does drive you, if you want to increase your certainty, towards a higher fidelity environment. Right? It pushes you towards those blade resolve solutions if you just don't have as much experimental data to get some certainty, or potentially at least encourages you to stay within this CFD environment. Again, hopefully that addresses your question, but I think it's a good point, right? At this point we don't know. We can have conjecture about it and good informed discussions, but it's difficult to say 100%.
Yeah, understood. Thank you.
And thank you very much.
If anybody does have any more questions, again, there's a lot more in the paper. And if you have any more questions, feel free to email them over, and be happy to carry on discussing.
Oh, fantastic. Thanks, Dr. Peters, and thanks everyone for attending. I think